All right, let's take a look at everything we learned in rational functions. The first thing we learned is how to sketch a graph when it is in transformational form. Remember, there's a difference between transformational form and general form. When it's in this form where you can identify A, H, and K, then you just move your graph around. So what sort of shift do we have here? Looks like we're moving right 2 and up 3. So when we sketch that going right 2 and up 3, you move your asymptotes. So the normal asymptote at 0 has been shifted right 2. The normal asymptote at 0 has been shifted up 3. And then we have a couple of key points. So your key points, from where the asymptotes cross, we go up 1 over 1. There's our turning point. And then we draw the 1 over x graph. So it's just been shifted. Same thing on this side. Go to where the asymptotes cross, left 1, down 1, and that should be the turning point. Okay, that's a little bit awful. Let's see if we get a better graph over here, and these were the 2 points we were talking about. Okay, let's look at the next one. What happens here? No shift, left or right, but we're going up 5. And then what does this do? We're going to stretch it, and we're going to flip it upside down. Okay, let's see if we can do that. So we don't shift left or right, so the asymptote is still at 0. We're going up 5. 1, 2, 3, 4, 5. So an asymptote up 5. Normally we go right 1, up 1, but this -3 is going to change things. So instead of right 1, up 1, it's right 1, down 3. That would be our turning point, and our graph is upside down. On the other side, normally we go left 1, down 1. We're going to go left 1, up 3. There's our turning point, and again, graph is upside down. For those who did not like that method of finding those 2 points, what we did as well is we said, where is the vertical asymptote? The vertical asymptote is at 0. Pick a point on either side of 0. If we plug -1 in, I get 3 plus 5, which is 8, which should be this point up here. If we plug 1 in, we get -3 plus 5, which is 2, which should be this point here. And a much better version of the graph. And there's our point 1, 2, and -1, 8. So remember, you do this when the graph is in transformational form. If absolutely everything is over the denominator, don't do this method. Okay, you learned how to match graphs. Matching graphs, you find asymptotes and intercepts, and that should easily identify your graphs for you. We practice simplifying expressions. First thing we want to do with this one is factor. We have all sorts of quadratics that will factor. And then if you're dividing by a fraction, you multiply by the reciprocal. And then look for like terms on top and bottom. Keep in mind that you must identify what x cannot equal at every step. Anything that spends any time in the denominator cannot equal 0. So that's where those ones came from. And an extra one from here when we multiplied by the reciprocal. So make sure you've got all your restrictions. All right, what's common? We can get rid of those. We can get rid of these. And the -2s, x minus 2. Okay, that's a much simpler expression. And again, state all restrictions, because otherwise this expression is not the same as what we started with. The top one had lots of restrictions, so we have to identify those to keep these the same. Solving rationals, we do something very similar to what we did earlier. Start by multiplying by the common denominator. So what's your common denominator? Denominator of x and x plus 3. So the common denominator would be x times x plus 3. Everything gets multiplied by that, and then reduce where possible. What should happen in this step is every denominator should be eliminated. Looks like they're all gone. So let's see what we're left with, and then we'll expand these, getting an x squared and a 3x, a 2x and a 6, and an x squared. Okay, collect your like terms. We've got an x squared on each side of the equation, so we can get rid of those. And then solve. Remember, after you state your answer, that you check your restrictions, because occasionally you'll have a restriction that appeared as an answer and we have to get rid of it. So in this situation, our answer is -6/5 with restrictions of 0 and -3. Then we sketched a graph in general form, everything over the denominator. Started this one by factoring. Is there anything we can reduce? Looks like it. And when you reduce, make sure you state your restriction. Otherwise, the two functions are not the same. Then we find x and y-intercept. X-intercept, you let y equal 0. The only way for a fraction to equal 0 is if the top equals 0. So x would equal 3. Y-intercept, I tend to go to the original. Just let all the x's equal 0, and it looks like we have -3/2. Then asymptotes. Vertical asymptote, what are we not allowed to have in the denominator? What would make that equal 0? Horizontal asymptote, there was a rule. You compare highest power in the top to highest power in the bottom. When they match, we divide them. X squared divided by x squared is 1. Any points of discontinuity? What was x not allowed to equal? And where is the -1/3 coming from? When you let x equal 1, I'm getting -2/3. So good question, where is that -1/3 coming from? I think that's a -2/3. Can't really read that, but we'll fix that. Check -2/3. Okay, let's check our graph, and that looks more like -2/3 than -1/3. So vertical asymptote, -2, horizontal asymptote, 1, x-intercept at 3, y-intercept -3/2. We connect those, and then we put a hole for the point of discontinuity. And then, of course, we remember there's something on the other side of the equation. And we remember that if we are negative on one side of the asymptote when you cross, it should start as positive. Solving an inequation. Start by letting y equal the expression and do exactly what we did in the last question. We'll factor. Doesn't look like we can reduce anything. Find x and y-intercept. X-intercept. If a fraction equals 0, it's the top that equals 0. So 3 and -2. Y-intercept, I tend to go back to the beginning. I'd get 3/2 for that. Asymptotes, what are we not allowed in the denominator? -4 and -1. Horizontal, compare the highest power on the top with the highest one on the bottom. They match again, divide them. There's our 1. All right, let's take a quick look at the graph before we look at the nice version of it. Vertical asymptote, -4. Vertical asymptote, -1. Horizontal asymptote, 1. Are there any points that we know? Because that's what we look at next. I have a point at 3. So we cross here and we cross at -2. A y-intercept of 1.5, that would be here. I'm pausing for a minute because something's gone badly wrong. Let's see. This x-intercept can't be right. We factored it incorrectly. +3, -3. So it's actually not a bad thing to look at a graph gone wrong. So this is useful. We were drawing this and we went, wait a minute, this cannot be right. We can't have a graph up here and down here. So that gives us a chance to check our work, realize we'd factored incorrectly and had the wrong x-intercept. So it's actually good for me to show you things that go wrong. So let's just back up and we'll start the graph over now that we realize we had a mistake on there. And we'll draw the graph again. Okay, let's try that again. X-intercept. Factor those properly. So x-intercept of -3 and -2. So those are 2 points on the graph. Vertical asymptote at -4. Vertical asymptote at -1. Horizontal asymptote at 1. And y-intercept of 3.5, 3/2. Okay, let's see if we can draw this properly. Start with the point that you're 100% sure of. 100% sure that the graph looks like that. How did we know that? We had to approach the asymptotes and we had to press through that point. We're 100% sure this is incorrect because we'd be making up x and y intercepts. On this side, what happens? Positive on the right side of the asymptote, therefore starts negative. So we start negative, go to that x-intercept, pass through the other x-intercept, and come back down. Now, two ways of knowing where to draw the graph. On the left-hand side, negative on this side of the asymptote means we're positive on the right-hand side, so our graph has to be there. We also know the graph has to be there because if we tried to draw it down here, we'd end up crossing the x-axis, and we can only cross at the x-intercepts. All right, so there's the lovely version of the graph. And would I take this? Yeah, I mean, you're doing the best you can, so it's a little untidy, but this is our aim. And we have to keep going. We haven't actually solved the question yet. We were doing an inequation. So where is y greater than 0? Let's take a look. Greater than 0 is anything above the x-axis. So remember that you split your region into 3. Anything above that is y greater than 0. The other sections on the x-axis and below the x-axis. We wanted greater than 0, and that's why we're picking this section. All right, so how do we describe that section? Where does it start and where does it end? Goes all the way to minus infinity. So minus infinity is the starting point. Sorry, having a little bit of trouble here. There we go. So minus infinity is where that region starts, and it ends at minus 4. We know we can never get to minus infinity, so that's a round bracket, and we don't have a single equal sign here, so everything's round. We also knew we couldn't get to negative 4 because it's an asymptote. This region starts at negative 3, ends at negative 2. Because we are greater than, no equal signs involved, they're all round brackets. This region starts at negative 1 and goes all the way to infinity. All right, so just be careful on these. A lot of people like to draw the graph and think, whew, I've done a lot of work, I should probably stop. So make sure you remember to actually finish solving the question, telling me where it's greater than 0. And let's check these answers, and we look good. Okay, lots of practice exercises for you. Good chance to solidify this knowledge. We'll be using all of this again in calculus, so make sure you're good at it. Have fun.